Gold is still quite the sought-after metal today, with the industry generating almost 200 billion USD in revenue every year. The first step is to identify potential gold-bearing areas. Geologists and mining companies conduct extensive surveys, prospecting, and geological studies to pinpoint areas with promising gold deposits. This may involve analyzing geological maps, conducting soil sampling, and using advanced techniques like remote sensing or geophysical surveys. Once a potential gold deposit is identified, the site is prepared for mining operations. This involves clearing vegetation, constructing access roads, and establishing infrastructure like camps and facilities. After the site has been prepared, it's time to mine gold. Most gold comes from lode deposits, also called vein deposits, the concentration of gold and other metals in the cracks of rocks. These deposits require hard rock mining, the process of removing gold-bearing rock called ore by drilling and blasting. Miners descend more than half a kilometer on the ground, and along with them goes specialized machinery made for the drilling process. The drilling equipment consists of a long-hole drill rig, which typically includes a drill steel, a long hollow tub, a drilling machine, and a source of compressed air. The long-hole drill rig is positioned in the desired location underground. The drill steel is inserted into the rock or ore face, and the drilling machine starts rotating and simultaneously feeds the drill steel into the rock. Compressed air is forced through the center of the drill steel to assist in removing the drill cuttings from the hole. The pattern and layout of the drill holes are designed based on the specific mining plan and the characteristics of the deposit. These plans are prepared by mining experts and geologists employed by the mining company. Factors such as the size, spacing, and angles of the holes are determined to optimize fragmentation and ensure the safety and efficiency of the blasting process. After the drilling is complete, the drilled holes are prepared for the explosives. This includes cleaning the holes of any debris and installing various components like stemming, material that helps contain the explosive force, detonators, and initiators. Once all the necessary preparations are made, the explosives are carefully placed into the drilled holes, and the blast is initiated from a safe location. The explosion breaks up the rock or ore, creating fragments that can be easily handled, transported, and processed further. After blasting the rock apart with explosives, miners use what's called a mucking machine to transfer the ore to cars, headed to the main shaft and then above ground to the mill. The use of mucking machines helps streamline mining operations by automating the process of removing loose material which would otherwise require manual labor or the use of other equipment like loaders or trucks. The gold-containing material, such as ore or scrap, is first prepared by crushing and grinding it into smaller particles the size of gravel. A mill then pulverizes the gravel to the texture of beach sand. This is done to increase the surface area for subsequent chemical reactions. The factory then adds a water and cyanide solution to the pulverized ore. Another mill grinds it further into a mud-like pulp. This pulp flows into large settling tanks. The wet solids, being heavier, sink to the bottom. The water at the top drains to another area. Workers transfer the wet solids into an agitation tank and blow in air. This process is called aeration or air agitation. The purpose of aeration is to introduce oxygen into the slurry. The oxygen sets off a chemical reaction between the cyanide and the gold trapped in the ore, triggering the gold to dissolve and leach into the surrounding water. Once the gold cyanide complex has been formed and the aeration process is complete, the slurry is sent to drum filters for filtration. Drum filters are large rotating cylindrical filters with a porous surface that allows liquids to pass through while retaining solids. As a result, the water containing the gold is separated from the solid impurities. To recover the solid gold from the loaded solution, a chemical process called precipitation is employed. Commonly used precipitation agents include zinc, carbon, or aluminum. These agents react with the gold ions in the solution to form solid gold particles. This solid is then separated from the solution through filtration, but it still carries a lot of impurities with it. To further purify the gold, it goes through a process known as smelting. The filtered material, often referred to as gold concentrate, is mixed with flux materials. This includes a concoction of chemicals like manganese dioxide, fluoride, silica flour, borax, and sodium nitrate. Flux helps facilitate the smelting process by reducing the melting point of the impurities and enabling the separation of gold from other elements. The gold concentrate and flux mixture are introduced into a furnace, which is a specialized high-temperature chamber. Inside the furnace, the mixture is exposed to temperatures like 1600 degrees Celsius, causing it to melt. The smelter is rotated to ensure everything inside receives an even heat. The high temperatures effectively separate the gold from other elements present in the concentrate, such as base materials and impurities. The molten material separates into distinct layers based on their densities, with the gold sinking to the bottom due to its higher density. The impurities, known as slag, float to the surface. Workers collect the slag, and a sample is taken to ensure it carries no gold. If it does, it's poured back into the smelter until it is completely gold-free. Once the gold has settled at the bottom of the molten material, it is collected by tilting or pouring the molten mixture. The gold is typically poured into molds or casts, forming what is known as a doré bar or bullion. It's interesting to note that the doré bar or bullion obtained at the end of the smelting process is only 80% pure. To achieve the international standard of gold purity, 99.9%, the gold still needs to be further refined. Once the gold has been refined, it undergoes assaying, which is the process of determining its purity and quality. Assaying is typically performed by specialized laboratories using various analytical methods, such as fire assay, atomic absorption spectroscopy, or mass spectroscopy. The refined gold can be further processed into various forms depending on its intended use. It may be shaped into bars, coins, jewelry, or used in other industrial applications. Adhering to environmental regulations and guidelines is crucial in cyanidation processes since the chemical carries grave environmental risks if not properly managed. Quality control procedures ensure compliance with environmental regulations and guidelines, preventing the release of excessive cyanide or other contaminants into the environment. Effective effluent treatment and waste management processes help minimize the environmental impact of the cyanidation operation. Although their names are interchangeably used, cement and concrete are entirely different products. In fact, cement is one of the primary raw materials used in the production of concrete, along with water and aggregate. The process of concrete making starts with making cement, the crucial binding material that holds the water and aggregates together in concrete. There are many different kinds of cement, but the most commonly used is ordinary Portland cement. It was named by its inventor as such because its color resembled the stone quarried on the Isle of Portland in Dorset, England. The primary raw materials used in cement production are limestone and clay. They are typically obtained from quarries by blasting or using heavy machinery to extract them from the Earth's crust. The extracted materials are transported to the crushing plant, where they are crushed into smaller pieces. The crushed limestone and clay are then mixed in appropriate proportions to form a raw meal. The raw meal is transferred to a mill, which consists of a large rotating cylinder. Inside the mill, the raw materials are ground into a fine powder. This grinding process enhances the efficacy of the subsequent chemical reactions and ensures the uniformity of the raw meal composition. The powdered raw meal is then heated in a preheated tower, where hot gases from the kiln are used to raise the temperature. As the raw meal moves through the preheater, it undergoes partial calcination, which means that some of the carbonates in the limestone decompose to form calcium oxide, lime. The preheated and pre-calcined raw meal enters a rotary kiln, which is a long cylindrical furnace. The temperature in the kiln reaches around 1450 degrees Celsius or 2642 degrees Fahrenheit. In the kiln, the raw materials undergo a series of complex chemical reactions and sintering, resulting in the formation of small, marble-sized nodules called clinker. The clinker consists of calcium silicates, aluminates, and ferrites. The clinker is discharged from the kiln and passes through a clinker cooler, where air is blown through it to reduce its temperature. Cooling the clinker is important to maintain its quality and prevent the formation of undesirable crystal formations. The cooled clinker is then ground with gypsum and other additives such as fly ash, slag, or pozzolana in cement mills to produce fine powder. Gypsum is added to control the setting time of the cement. Once prepared, the cement is ready for transport to the concrete factory. Because cement is such a crucial part of concrete, cement plant laboratories check each step in the manufacture by frequent chemical and physical tests. The labs also analyze and test the finished product to ensure that it complies with all industry specifications. Now that the cement is ready, it's time to source the aggregate. Aggregate is the most important component of concrete, comprising up to 75% of concrete by volume. When it comes to composition, aggregate is composed of both gravel and sand. The sand is added so the spaces in between the gravel are completely filled, thereby giving the concrete stronger bonding and consistency. A well-graded aggregate, which is a balanced mixture of coarse and fine particles, reduces the requirement of cement, thereby making the whole process much more cost-effective. Now is a great time to talk about the hidden stars of concrete manufacture, the admixtures. These chemicals offer a range of advantages and may be added to concrete to improve its properties. Plasticizers give the concrete greater workability, which refers to its ability to be easily molded and placed without segregation or excessive bleeding of water, allowing it to reach congested areas. Accelerators or retarders are another type of admixture that fasten or slow down the setting time for concrete. Due to the fact that concrete cracks under tension, many chemical additives have been developed to increase the tensile strength of concrete. Concrete may also be strengthened by using fibers made of stainless steel, glass, and carbon. With the raw materials all there, concrete production can finally begin. The first step is to measure the proportions of cement, aggregate, admixtures, and water based on the desired strength and characteristics of the concrete. In fact, concrete mix design is an entirely different discipline dedicated to finding out the right proportions of raw materials in order to reach a target tensile strength. Moreover, building codes have been developed that specify the ratio of cement, aggregate, and water based on the different types of construction. The next step is to mix the ingredients thoroughly to create a uniform mixture. Traditionally, this was done manually using shovels on a flat surface such as a concrete slab. However, nowadays, concrete mixers are commonly used, which automate and speed up the process. The mixing process ensures that the cement particles are evenly distributed throughout the aggregates. Once the dry ingredients are mixed, the water is added gradually while continuing to mix. When water and cement are mixed together, a paste called cement paste is formed. The hydration process generates heat and continues over an extended period, gradually increasing the strength and durability of the concrete. The mixing process continues until the concrete has a uniform consistency. During this step, it's important to check the workability of the concrete. The consistency of the concrete can be adjusted by adding more water or dry ingredients as necessary. Once the concrete is mixed and has the desired consistency, it is transported and placed in its final location. This can be done by pouring it directly into formwork, molds, or by using specialized equipment such as pumps or conveyors. During the placing process, it's important to avoid segregation, which is the segregation of coarse aggregates from the rest of the mixture. After the concrete is placed, it needs to be properly compacted to eliminate any voids or air pockets. This is typically achieved using vibrators or by mechanical means such as tamping or rolling. Compaction ensures that the concrete is dense and has good strength and durability. Once the concrete is placed and compacted, it needs to be cured. Curing is the process of maintaining adequate moisture and temperature conditions to allow the cement to hydrate and gain strength gradually. This typically involves keeping the concrete damp or covering it with curing membranes, blankets, or plastic sheets. Curing can last for several days or weeks, depending on the type of concrete and the desired strength. After the concrete has cured sufficiently, various finishing techniques can be applied to achieve the desired surface texture and appearance. This can include techniques such as smoothing, leveling, troweling, or applying decorative finishes. Owing to its versatility, cement is the most widely used construction material. In just the United States, over $4 billion worth of hydraulic cement, a variety that hardens underwater, is produced annually for use in $20 billion worth of concrete construction. Globally, the concrete industry is estimated to be over $600 billion, which, trust me, is a lot of zeros.